Hello friends, I am MB. Now I am going to discuss like a symbolic computing SYMPY. This is used in a Python programming language. So symbolic computing is an entirely a different paradigm in the computing compared to an numeric array based computing introduced in a previous like a already I have discussed look like a numpy. So in symbolic computing software it is known as the computer algebra system CAS. Computer algebra systems representation of a mathematical objects and expressions are manipulated and transformed analytically. So it is mainly about using computers to automate analytics computations that can in a principles be done by hand with a pen and paper look like. So analytical and symbolic computer it is a likely a part of the scientific and technical computing landscapes, and even for a problem that can only be solved numerically is common because analytical methods are not feasible in the many practical problems. So just it can make a big differences to push the limits, and for we can be done analytical before the restoring the numerical techniques. So let's see the scientific. So Python environment is the main module for the symbolic computing SYMPY. This is a symbolic Python. Symbolic Python. So it is written in a Python and it provides the wide range for analytical and symbolic problems. So mostly keep in your mind just like it is a wide range of analytical and symbolic problem. So it provides tools look like this one. So let's see just SymPy, we can say the SymPy. So it is library. So first I am going to import a SymPy. So import rt import sympy. So SymPy project provide a Python modules named SymPy. So SymPy as a modules names. So SymPy project provides the Python module name SYMPY, and it is common to import all symbols from these modules when working with a SymPy. So using from a SymPy import, okay. So now, but if one other thing, just you can also from SymPy import and stars. This is the other way you can import here other package numpy, say scipy. Okay, we will see in later. And now here we have a called sympy.int underscore printing functions, which configure a SymPy printing systems to display nicely formatted renditions of mathematical expressions. So SymPy and this one. So let's see, just I am going to here from SymPy and py from SymPy import integer as a I comma pi comma 0 0. I think it is look like also this one from MP, and I think not a 0 0. It is look like a 00 5 and 6. Yeah. So for convenience or readability for the examples codes, so we will assume that the following frequency look at user symbols, this one. Something just keep in your mind, NumPy and SymPy as well as the many other libraries provide the many functions and variables with the same name, but these symbols are rarely interchangeable. So numpy.py is a numeric approximations of the mathematical symbol pi, and while the sympy.py is a symbolic representations of pi. So it is therefore important to note mix them up to use. numpy.py is a place of the sympy.py when doing a symbolic computations or vice versa. Same holds true and the many fundamental mathematical functions like sine via sympy dot in numpy dot sine and sympy dot sine. So let's see, just I am going to write here one code. And one more thing, excuse me, sympy dot int means integer underscore printing underscore interesting. Here you write here the printing and parenthesis, so it has been also need to the SymPy printing systems to display the nicely formatted renditions of mathematical expressions. Look here, so integer and printing. So let's see, just I am going to write here x will equal to sympy sy mpy dot symbol symbol. So just look here, x will equal to sympy dot symbol sympy dot symbols and symbol. So you can have symbol and now write here 1 x as a variable. So the variable x now represent an abstract mathematical symbol x, of which a very little information is known by a default. So you can look here the print x, print and here x. So this print here, so only it has been printed look like x. Now similarly, just I am going to write here another, look like I am going to print y will equal to sympy dot symbol bracket start parenthesis just y and real equal to 2. Okay, so y is real. So if I go to print look like this, and if I want to ask the question y is real, yeah, it has been printed look like, and another I am going to print here y dot is underscore real underscore real. Okay, so you are asking a question, so your output will be yes. Now it is a true. Similarly, x dot is real is known is also the other way. So if on the other hand, so we were use is real, so x dot is real. Same thing, just in which the is underscore real attribute as a look like a imaginary. So you can write here, so z, so because you don't have the any z, so you write here sympy dot symbol, and now z as a one variable, but now imaginary image NARY RY will equal to true. Dot is real. So because z I have not created, so it has been seen like a value this one. Similarly, we can also write here is positive is real. Similarly, is positive is negative. Okay, so we can easily create look like this. Is odd is even, is prime, is finite, is infinite. So this is it, look like this way. So this is a way. So let's try. I am going to write here v, and if I write here real and imaginary, and I write here look like positive, okay, false. If you write here negative, right? So because specified that the symbols is a positive or a negative, false. And if you write the integer, integers, so is integer, so this one is a false. Is odd is even, so similarly we can also is prime is finite, so let's try here is infinite, infinite, false, is finite, is finite. So the symbol represents a quantity of the finite infinite. Yeah, is finite, yes, it is true. So I hope assumptions, keyword, arguments, and I have already discussed some selected assumptions and their corresponding keywords for a symbol like object. Now another, just I am going to print here some value like a x will equal to sympy dot symbol and this one is a x inside of this x, and another I am going to the print of y will equal to sympy dot symbol and create here y and now positive will equal to 2. Positive will equal to 2. And another I am going to write here third value look like this sympy. So first I want to print and x comma y. So it has been printed look like this. But if I write here symbols will, so you can write the sympy dot sqrt means square root sqrt as a square root and start here brackets parenthesis and I am going to write here double star and 2. So let's see square root and it has been printed like a under root square root. Similarly we can also print sympy and squared as a y. So you can write here yt any other variable because I have already taken as a variables y, so we can easily create here y sqrt and double square dot sqrt, but it has been printed only y. So sympy dot sqrt and y square. So why it looks like a difference? So here we have created the two symbols. One is the x, another is y, and computed the square root of the square of the symbols using the sympy functions sympy dot sqrt and the symbols in the like a computations. But then no simplifications can be done. So if on the other hand the symbol is known to be representing the positive number, and then obviously under root y square will be y, and simply correctly recognize this is a different way. So when we are we are working with a mathematical symbols, the representations integers and rather than say the real numbers, it is also useful to explicitly specify this when creating the corresponding sympy symbol using look like an integer. Just you can say the true, and even true or odd you can also write a true. So see here, look here, just if I am going to print n1 will equal to sympy dot symbol and another value like a n, and now the another value n2, just you can read sympy dot symbol and it can represent here n. Now integers, integer will equal to 2, and third we can also write here n3 will equal to sympy dot symbol and now n and odd will equal to 2, odd will equal to 2. So there are 3 variables, and now I am going to the sympy dot cos as a trigonometric functions, and I am using the first variable n1. This will multiplied with a pi, so I write here pi. So let's see what happened. Just simply symbols n, and it has been printed cos pi n. Similarly, I can also write here other functions look like a sympy dot cos bracket start. Now n2, I have already created a variable, and pi, because n2 look like a n and integer true, so integers and true, so I have taken here the integer, and n2 into pi means it has been created -1 to the power n. But if I write here sympy, so and n3, just n3 and pi, so look like a n3 variable, n means odd and true, so you can write -1. So now I am going to formulate a non-trivial mathematical problem, and it is often necessary to define the large number of symbols using a symbol to specify each symbol one by one may become tedious, and you can say the convenience. So sympy contains a function sympy dot symbols for creating a multiple symbols in a one functions call. So this functions takes a comma separated a string of a symbol's names as well as an arbitrary set of keyword arguments, and it returns as tuples of the newly created symbols. So using Python tuples, unpacking, just I have already discussed syntax together with a called a sympy dot symbol. So unpacking means we can take a more variables. So on a comma b comma c, and all 3 variables will equal to sympy dot symbol, and I am taking look like a comma b comma c and comma negative will equal to 2. Similarly, now I am going to take here second variable def, d comma e comma and f. here G E F, right. Now again you write here SymPy dot symbol SymPy dot symbol and bracket start. I have created like a string D comma E comma F comma positive will equal to true. Positive will equal to true. So just both has been created and we can easily print. So the purpose of representing the mathematical symbol as a Python object is to use them in an expressions tree that represent a mathematical expression. And now we have to be able to do this. We also need to represent the other mathematical symbols such as numbers, functions, constants. So we can easily print one by one. So I think just a negative A has been created and error, so it has been created, cannot unpack a non-iterable symbols object. So using a Python tuple unpacking syntax look like this way, and A comma B comma C. So let's see. Yes, it is A2. You can see that something. Yeah, otherwise you can see like this. A comma B comma C, and it has been, I think, symbolic. So cannot unpack the non-iterable. So A has been taken as this. So now A, I think, SymPy SYMPY dot SYMBOL. Oh, sorry, symbols. It should be here the symbols. I think because not as a symbol, because more than one. So now it has been like this. Is it SYMBOLS? Too many values to unpack. Created like this, and A comma B comma C. So too many values is unpack expected 3 A comma B comma C. So the SymPy dot SYMBOLS. It is possible. Sometimes my internet is not working, so it may be possible. So, but I don't think. Okay, let's see. Don't worry. Just I will try to solve after some time. Otherwise, I will write the sum. Right. There is the true. It has been written. Look like, oh sorry. I think I have gotten this mistake here. So your colon, yeah, must be right there. So similarly, I think your colon must be, so this work, yeah, right. Yeah. So I hope D comma E comma F has been done, and now D comma E comma F, and this one is a positive. So let's see, just a positive will equal to true, and you keep here go. So modules SymPy has no attribute SYMPOLS, so like this way, or I can just SYMVOL comma E comma F. So need to give a space, some space, okay. Then here colon has been positive, I think here, yeah, positive, and double quotations have been given. So yeah, first code is a working, so second is not a working. Module SymPy dot symbols, exactly just I have written the capital letters, so keep in your mind. So these are the very simple and the basic, so you have to understand, just you are doing this type of the programming. So now I am going to print A. So yes, it is possible to, you can also print A and something B and C also, so doesn't matter, D, E, F. Okay, so now the next start here the numbers. Yes, sometimes you can get some bugs, it is to learn more and more. So now let's see here the integer and the SymPy dot float, and use the sum their attributes to the query of their properties. So let's see, I will equal to, if I write here I will equal to SymPy dot int dot intger, and right here 90 20 something, and what type of integer, so you need to understand type. So type of I means, let's see, so type SymPy dot code dot number dot integers. So I is integers, I is real, I is odd. So you can ask I dot is underscore integers integer. Similarly, if I want to write here I dot is real, so you need to put here comma, dot is underscore real comma I dot is underscore odd. So you can ask any questions, just is odd. And now let's see a print. So integers, so I as a variable I have taken, so S it is an integer, S it is an real, and it is an odd value because 19. But if I put here the 20 and you ask the same question, let's see, so you can get here and you are asking the same questions. So look here the last, because it is not odd, so it's like a false. Same, now I am creating another variable, f will equal to SymPy dot float and because float value, so you can read here 2.3 something. And now ask the question here, type has been printed as a f type, so look like sympy.code.number.float. Similarly, same questions I can ask from here, because I have taken a f as a variable, so look like here, so I can replace f here, I can replace here f here, I can also replace f. So let's see, just I am going to f as a variable, so it is an integer, it is an real, and now it is 2.3 is not odd, so you can see here false. So we can cast instance of a sympy dot integer and sympy dot float back to a Python and build in a types using a standard types casting job like a int plot f. Okay, so there is a alternative way we can easily represent I and n. So now we can also simply represent of a numbers or in a general attributes expressions. So we can also use a simply dot simplify functions, and these functions take in a wide range input and derive as a simply computable expressions, like it eliminates the need for specifying it explicitly. So what types of objects are to be created? So just unpacking look like a I, J, here you can see right here F, and there are two variables. We can write simpy dot sim sympy sympy simplify like a 19 and comma I am going simply dot simplify and I am writing here float value 2.3. and now I want to know here type I and comma type f. So let's see, just both I and f, sympy okay, pify 19 sympy dot sympy, okay, please not don't write the please SymPy. So let's see, just okay, again just look like this, I and f module simply has no attribute, sympy simplify. So type I and type has been printed, so something has not a clear to. So let's see. I hope it is possible to I and F. Is it clear? Now I have written here the equal sign SYMPY dot is okay, not a simplify SYMPIFY. So SY, same mistake, just SY, simplify. So simplify, so now it has been created both of them once. Same thing, just you can use here the integer and the others way also. So you can write here n will equal to sympy dot symbols and n integer true, and we can easily ask the questions. N is an integer, n is a integer, n is a positive, n is a symbols, so you can get answer. And same types of the numbers you can write here, some integers, and you can ask the number of the questions. But the integer in a SymPy are attribute and precisions, meaning that they have a no fixed lower and the upper bound, which is the case when representing integers with a specific bit size as a like a numpy. So if I write here just one more thing, I, and I need to write here just like here, I need to the multiply 50. So it is possible, yeah, you can get any output, try, so right. So I have gotten here output. Similarly, just I am going to write here, so you have got a look here, just output, yes, exact. Similarly, I am going to sympy and dot factorial. So just like a 2 factorial, 4 factorial, 5 factorial, you can write the 4 factorial means 4 into 3 into 2 into 1. So 4 factorial, so I need to count factorial 100. Is it possible to count here? So let's try the sympy dot factorial, and it has been created in few seconds. Look here. So you can get in all these numbers. So these are the very beautiful to understand as a most of the science student. And now just look here the how to means can I write here the any rational numbers. So you can write here sympy dot rational in L, and just write here 12 comma 13. Is it possible to write here? So simply look like, yeah, just it has been written. Similarly, we can create the two variables and we can easily multiply and get the fractions. These are the very beautiful. So this is a way to understand. So let's see, just I am going to create here the one variable, look like now p will equal to this variable, and second variable I am going to write here look like this v, and here is and the pq, right. So there are two variables, and now I want to the multiply p into q. So p and now a star and q here. So is it possible to get your answer? Absolutely, you can easily multiply, and you have gotten the value 12 into 12 144, and this is the denominator 13 into 13 69. So is it possible to divide here? Yeah, it is possible. So p also is divided by q, look like a q, So look here the forwarded space here, right here. So yeah, I have gotten here 1 means whenever if you divide p by q, so you can get here 144 by approx value, just it has been gotten here approx. So sympy dot pi, sympy dot e exponential, sympy dot Euler gammas, sympy dot I means imaginary units, and sympy dot infinity means double O as an infinity. So we can easily get here. Next time I try to discuss functions. So how to create a functions in a SymPy, and expressions is also just here. So expressions we can create in the most of the algebraic linear expressions, and I hope it will be benefit for someone. Okay, thank you.